Hello everyone. Now today we are going to discuss about fundamentals of the AC. That is, we'll discuss few definitions. What is an AC waveform and what are the ways by which we define the AC waveforms. An alternating current or voltage, that is our electrical quantities, is the one which changes periodically both in magnitude and direction. Such change in magnitude and direction is measured in terms of cycles. That is, from where it starts and starts repeating itself, that particular time period is known as one cycle. So each cycle of AC fundamental consists of two half cycles, namely positive and the negative cycle. The magnitude increases, then comes to zero, again attains the negative maximum, comes to zero, and then it repeats itself. So that is the peculiar way of the sine waveform, and that is what has been shown in the figure for the voltage signal. We have got the sine wave. The amplitude is defined as the maximum value attained in the positive half or the negative half. That is known as the amplitude of the given signal. The time taken to complete one cycle is defined as the time period, and the peak to peak voltage is from the positive peak to the negative peak is known as the peak to peak voltage. Now we'll define the few terminologies, that is the instantaneous value. What is an instantaneous value of an alternating quantity? At any given instant of time, the magnitude of that given waveform is known as the instantaneous value. The definition is the value of an alternating quantity at a particular instant is called its instantaneous value because it's continuously changing in magnitude with respect to time. Therefore, the instantaneous value will be different at a given instant, and that value is known as the instantaneous value. Next term is cycle. Each repetition of a set of positive and negative instantaneous values of an alternating quantity is called a cycle. That is, from where any point in a given signal, you take a reference point, and from where it starts repeating itself, that particular time, one cycle is known as that it has completed one cycle. The signal has completed one cycle once it starts repeating itself. And the time taken to complete its one cycle is known as its time period. The time period is denoted in capital T and the unit is seconds. Frequency. What is frequency? The number of cycles completed by an alternating quantity in 1 second is known as its frequency. It's denoted by small f and the unit is cycles per second or hertz. As the time period is given by capital T and therefore f is the inverse of time period, that is f is equal to 1 by t. Amplitude, the maximum value attained by an alternating quantity during positive or negative half cycle is called its amplitude. Now I have given some examples of an alternating waveform. Normally sine wave is taken as the most common waveform because that is what is generated in the generator units and transmitted and distributed in our household appliance for the household utility is the sine waveform. That's the reason the sine waveform is so common in use. But whatever we have shown as the other waveforms, the square waveform, the triangular waveform, or not exactly sine or cosine, but it is some complex waveform, that is also an AC waveform. So it's not necessary that it has to be a sine waveform. Anything which is alternating from positive to negative, negative to positive, it has got only positive, but still it is changing its magnitude and direction. That will be known as an AC waveform. Now here I have shown the figure as how the AC voltage is being generated. The AC voltage generated is, you have got a magnetic field. The coil is placed in the magnetic field, and when the coil cuts the magnetic field, the EMF is being generated, which is given by E is equal to d phi by dt, or with the help of the Lenz's law, the direction also is given by E is equal to minus n d phi by dt. That is, the Lenz's law says that it opposes the very cause which is producing it. So over here, if we see the first case, that is, the coil is in alignment with the direction of the flux. So the flux is passing through the coil, but the flux cut is maximum. Okay, the flux cut by the coil is minimum, but the rate of change of flux is maximum. Hence, the induced EMF is maximum. While in the second figure, the flux passing through the coil is maximum, but the rate of change of flux is minimum. Hence, the induced voltage is 0. Then, after 180 degrees, the coil has reversed its direction, and therefore, the voltage magnitude again produced is maximum, but now it's negative. Then again 0 and comes to the positive half. So this is one complete cycle generated by the given machine or the generator, where we have taken a simple permanent magnet, a coil, and when the coil cuts the flux, the EMF is being induced in the coil, and therefore we get a sine wave at the output. Now, how do you measure the magnitude of the AC waveforms? So one is the average value, the other one will be the RMS value. The average value is the area under the curve is known as its average value. Now for an AC waveform where the positive half is equal to the negative half, the average value of the complete cycle will be 0. Hence, we take the average value of only one cycle and not both the cycles. Over here, what we have taken for an example is, if it is an irregular waveform, in that case, you can use the mid-ordinate rule to calculate the area under the curve. To calculate the area under the curve, mid-ordinate rule, you pick up some instantaneous values and add all the instantaneous values, dividing by the total number of the instantaneous values. So that gives the average value. So the average value is a one term by which we define the magnitude of the AC waveform. Next is the RMS value. Now RMS value is more important in terms of AC, because when we say we are getting a 220 volt supply, that is referring to the 220 volts RMS value of the given waveform. Why is RMS value so important? Because it is equivalent to the DC quantity which will produce the same heat. Like suppose you have got a given element and a DC value I is flowing through that given resistance. Therefore, the heat produced will be given by I square R into T. Now, the equivalent of that DC current which produces the same heat by giving an AC supply is known as the RMS value of the given AC. Now, how to calculate the RMS value? The RMS value is root mean square. So first we square the terms, then take the mean of it, and the square root of the total value gives us the RMS of the given waveform. In the previous case, where we have taken some irregular waveform, in that case, you'll take again the mid-ordinate rule. Take the square of the instantaneous values, take the mean of that, square values, and then whole under root will give you the RMS value. But for a sine wave, we define it by the equation. Now the mathematical way of defining this sine waveform is given by V is equal to, because we have taken a voltage equation, so voltage equation will be given as V is equal to Vm sine omega t, where Vm is the amplitude of the given waveform, that is the maximum or the peak of the voltage or on the positive or the negative side. Omega is its angular radiance, so that angular speed will be given by 2 pi f, where f is the frequency of the given signal and t is the time in seconds. So V will be given as Vm sine omega t. Similarly, an alternating current can be expressed as I is equal to Im sine omega t, where I is the instantaneous current and Im is the maximum or peak value of the current, that is the amplitude of the given current signal. Now, how to calculate the average of the sinusoidal waveform? For calculating the average of a sinusoidal waveform, because we have got the equation of that sine wave, hence we can integrate that for a given time period and take the average of that. So the mean value means we are taking for the half cycle, because full cycle will again have the average value as 0, because the positive half and the negative half are equal. So they both will cancel out and the total average value will be 0. So for a sine waveform or a cosine waveform, or for any sine wave which has got equal positive and negative values, average values, there we take the average value of only half cycle and we calculate it. Therefore, the equation for the average value becomes as 1 by pi integration from 0 to pi Vm sine omega t d omega t. We are integrating it with respect to omega t, that is theta, and therefore the cycle for the period for the half cycle will be 0 to pi. Integrate it, put the values, and finally you will get the average value as 2 Vm by pi, which is equal to 0.637 Vm. The RMS value is given as same equation, but now it will be square, mean, and whole under root. That will give us the RMS value. So VRMS is given by under root of 1 by pi integration from 0 to pi Vm sine omega t whole square d omega t. Now substitute the values, integrate those, and then get the final value, where we get the VRMS is equal to Vm by root 2, which is equal to 0.707 Vm. So for a sinusoidal, pure sinusoidal waveform, the average or the mean value will be always equal to 2 Vm by pi, that is 0.637 Vm, and this relationship holds true for average values of current also. So the relationship between the RMS and the maximum value for a sinusoidal signal is given by VRMS is equal to Vm by root 2, or IRMS will be Im by root 2, that is equal to 0.707 of the maximum value or the peak value. So the RMS value of a sinusoidal waveform is always greater than the average value, except for a rectangular waveform. In this case, the heating effect remains constant, so the average and the RMS value for the square waveform remains the same. Now, two more factors we are going to define. One is the form factor, other one is the crest factor. Form factor is the ratio between the average value and the RMS value, and is given by form factor is equal to RMS value, that was for a sine waveform, it is 0.707 Vm, and average value is 0.637 Vm. So that comes to as 1.11. So this pure sine wave will have a form factor of 1.11. The other term is crest factor. Crest factor is the ratio between the RMS value and the peak value of the waveform. So for a sine waveform, the peak value is Vm and RMS value is Vm by root 2. So it comes to as root 2, and the crest factor for a pure sinusoidal waveform is 1.414. So we have defined the terms for the AC waveform as the instantaneous value, the time period, cycle, frequency, the amplitude, the average value of the given waveform, the RMS value of the given waveform, and then the form factor and the crest factor. Now we'll take some numericals where we have to calculate the average value and the RMS value. Now this is a step waveform we have taken for an example. In this step waveform, you have to calculate the average value and the RMS value. Now again, if we see the positive half and the negative half, both are equal. That is, we call it is as a symmetrical waveform. Hence, due to symmetry, for average value, only half cycle will be considered. So when you consider only half cycle, again, the area under the curve divided by the length of the base will be taken as the way to calculate it. So by substituting the values, you can calculate the average waveform. So average value of the given waveform and the RMS value of the given waveform, and the form factor for the given waveform comes as 1.19. Now another example is an alternating voltage has the equation as V is equal to 141.4 sine 377t. You have to calculate the values of the RMS voltage, frequency, and its instantaneous value at t is equal to 3 milliseconds. Now, as per the given equation, the maximum value is 141.4. Therefore, the RMS value will be the peak value divided by root 2, that will come out to 100 volts. Omega is 377. So that 2 pi f is given as 377 radians per second. Therefore, f will be 377 divided by root pi, 2 pi, which comes to as 60 hertz. To find out the instantaneous value, substitute the value of t in the given equation, and that comes out to be 127.8 volts. Now another waveform I have taken where you have got a ramp waveform which has got a time period of t, and it's completing its cycle in just for t1, and then it is 0 for t1 to t. So how do you calculate the RMS value of the given signal? For the RMS value, the signal will be given as the given equation, that is V RMS will be equal to under root of the time period 1 by t, 0 to t, integration, and the equation of the given signal with respect to time. Now for the given signal, the equation can be written as a straight line equation because it is crossing from 0, so no constants. It is only y is equal to mx. So what is the slope? M. Slope m is Vp by T1, and therefore the equation of the voltage will be given as Vp by T1 into T. Now substitute that in the VRMS equation, and you will get the equation as under root of 1 by T, 0 to T, Vp by T1 whole square T, and with respect to dt, you have to integrate. After integration, you will get the value of VRMS as Vp whole under root T1 by 3T. Now, another waveform, similar waveform, where the slope is just opposite, but the time period has been reduced to t with the cycle. So over here in this waveform, as compared to the previous waveform, t1 will be equal to t. That is the time period for which the cycle was existing. Same is the time period of the given cycle. So substitute over here as t1 is equal to t, and you will get the Vrms value as Vrms will be equal to Vp by under root 3. So this is how you can calculate the average and the RMS value for any given waveform, and you will be able to find its equivalent DC. That is, the RMS means equivalent DC, you are calculating it. So for any waveform, find out the equation, put into the Vrms value equation or the V average equation or current average or current RMS, and you can calculate its magnitude. Now next we will try to understand the phasor relationship between the two signals. Now to understand the phasor relationship, we'll take the sine waveform only, as we had learned before, to represent the sine waveform as A is equal to Am sin omega t, but that is when the reference is 0 or the signal starts from 0. Now if the signal starts instead of 0 towards the left side, the signal has been shifted towards the left side. When the signal is shifted towards the left side, this means that the value of the given signal at t is equal to 0 is having phi if the phase is shifted by 5 degrees to the left side. Then the equation becomes as A is equal to Am sin omega t plus phi. Now, next is, if the signal is shifted towards the right side, then at t is equal to 0, the value of the given signal is omega t minus phi, and it will attain its 0 after 5 angles. Therefore, to represent the signal which has shifted towards the right side is given as Am sin omega t minus phi. So the same signal can be also represented in the phasor form. That is, over here we are seeing two signals with the same 0 degrees reference, and that is given as V is equal to Vm sin omega t, I is equal to Im sin omega t, because both are starting from 0, so phi is equal to 0. While in the second figure, we see that one voltage signal is starting from 0, while the current signal has been shifted towards the right side. That is, the current signal is lagging the voltage signal by an angle of phi. Hence, in the equation form, we represent as V is equal to Vm sin omega t and I is equal to Im sin omega t minus phi. And in the phasor form, the V is the reference, so the x-axis represents the voltage, and I is lagging behind by phi, so it is taken on the negative side, and we show that the the current is lagging the voltage by an angle phi. Now over here, just we have taken a reference as the x-axis and tried to show you that if the signal is leading, the angle will be plus phi. If the signal is lagging, the angle will be minus phi. And the way you represent is, when it is a leading angle, then the angle will be positive, and so it will be taken as a positive angle. And if the signal is lagging, then the angle will be taken as negative, so it will be in the fourth quadrant. Okay, so this is how we try to represent in terms of phasors, because drawing the waveforms every time is quite tedious. Hence, we represent the phasor in the phasor form most of the times the given waveforms. The waveforms are represented in the phasor form instead of drawing the exact waveforms. Now, we have got different forms of representation of the AC waveform. In equation form, we have seen before, that is, we have taken the voltage equation as V is equal to Vm sin omega t, reference, and current may be leading or lagging depending on the circuit conditions. I will be given as Im sin omega t plus minus phi. If it is leading, plus phi. If it is lagging, minus phi. The polar form way of representation is much more common or much more in use because that is a simple form of representation as per the practical requirements. So V is given as capital V angle 0 and current is given as capital I angle plus minus phi. Now what are these capital V and capital I? These represents the RMS value of the voltage and the current respectively. And for a sine wave, we have seen before, that is the RMS value is maximum value divided by root 2, that is 0.707 times the maximum value. So the RMS value has to be taken in representation of the polar form. The same polar form can be also represented in the rectangular form as V is equal to V cos phi plus J0, because the polar form representation is the magnitude and the angular reference. While in the rectangular form, we represent in the form of real axis and the imaginary axis. So when the angle is 0, only the real part is present. But if there is some angle, then phasor angle, then you will have the imaginary part also, that will be represented as I cos phi plus minus I j I sin phi. J is nothing but the iota, because in electrical part we are representing current as I, so we represent the iota in terms of J. Now if you want the conversion from rectangular to the polar form, then I will be given as I under root of I cos phi square plus j I sin phi square, and that will give you the RMS value, and it will be can be used in the polar form of representation. And phi will be calculated as tan inverse of I sin phi and divided by I cos phi. Exponential form of representation is also there, which we represent as I e to the power j phi, and with the Euler's identity, we know that it can be written as I cos phi plus j I sin phi, which is the same as the rectangular form of representation, and that will be same equal to the polar form of representation as I angle phi. So these things will be used time and again in the AC calculations. So we should know all the forms of representation, how the things have been given and how it will be calculated. So thank you.